Well, this section is about integrating powers of trigonometric functions, and particularly sine, cosine, tangent, and secant. Those are the ones that we worry about the most. And so the first question that's posed is, how do we integrate sine to the fourth x times cosine x dx? And of course we would do this by substitution. And this is just kind of to whet our appetite. And the way we would do this, of course, is we would let u be sine of x. And in that case, du would be cosine x dx. And you see then our integral becomes the integral of u to the fourth du. And we can easily integrate that and go further. We don't need to do that here. Well, we're going to proceed to integrating the integrals of the form. That's what we're working on. Integrals of the form sine to some power times cosine to some power, things of that type. Now, normally one of those two powers needs to be an integer, a positive integer. But we'll look at different types of examples here first, or mention different types of examples, just to get an idea of what we're talking about. And we'll actually have several different categories, but these are all the same category. For instance, we might be asked to integrate sine cubed x cosine squared x dx. Or we might be asked to integrate sine to the fourth x, we just saw, cosine x. How about sine cubed x cosine cubed x, just as another example? Or how about the integral of sine, and I'm going to write this a little differently, sine to the x to the power 1/2 cosine cubed x with respect to x. Or a couple of other examples, and these examples have only one of the trig functions to a power. Okay, so sine cubed x with respect to x, or the integral of, say, like cosine to the fifth x with respect to x. Now, one of the things that may not be apparent as I've written these examples down, in every one of these examples, one of the two powers is an odd positive integer. We either have a power of 3, sometimes we have both of them as a positive odd integer, but in some cases, or we don't necessarily have to have them both as a positive odd integer. But in all these cases, there is, the secret here is that one of the powers, odd power of 1, is common here in all of these examples. Now, we'll talk about what happens when we don't have that situation, but when we do have that situation, we need to remember this identity. We're going to get to some examples here in a moment, but we're going to remember this identity. Certainly we know that sine squared x plus cosine squared x is equal to 1. And so in this case, we can actually solve for either sine squared or cosine squared. And the point of it is we can convert one, a power 2 of sine or cosine into the other function. That's an important observation that we make here. So let's take our first example, and what we'll do here, I hope I have enough room, example 1. Now we're going to use substitution. That's example 1. We're going to use substitution, and we're going to integrate sine to the fifth x cosine squared x dx. Now, here's what we're going to do is we're going to choose one of these two trig functions to be u. That is, here's what I mean. U is either going to be sine of x or u is going to be cosine of x. And as we investigate, we'll see what the problem is or what the issues are. Maybe that helps us understand how we accomplish this. Well, if we choose u to be the sine of x, then du would be cosine x dx. And there's nothing wrong with that, except we have cosine squared x, don't we? And if we let me point out to you, maybe on the next page I'll continue this actually. If we make this substitution, then what we're going to end up with, if this is the substitution we make, then our integral will be u to the fifth, and since we have cosine squared x, we would have a cosine x times a cosine x dx, and that would be our du. And we've still got this cosine x business left over, so that's a problem. We're not any better off. If, though, on the other hand, we let u be cosine x, we let u be cosine x, well then here's what could happen in that case. Du would be sine x dx. Now, that at first glance maybe looks like that's still a problem as well. But let's imagine what we would have if we did this. Our integral, here's what we're going to do. We're going to borrow one of those sine of x's. So we have sine to the fifth x, and we need a sine x dx for du. So we've got a u squared, because u is cosine x. And now our du is sine x dx. And so we need a sine x dx out here to make a du. See, that would be our du. But if we do, then we still have a sine to the fourth x here, don't we? Like I said, that looks like it's a problem. Here's why I say that looks like it's a problem. Is because we have sine to the fourth x, and now we have u squared du, and we still have sines. But here's the issue. Sine squared x is nothing more than 1 minus cosine squared x. And so that means sine squared x could be replaced with 1 minus u squared. But we have sine to the fourth x. So here's what we do. We say, oh, sine to the fourth x is really sine squared x being squared. And sine squared x we've written as 1 minus u squared. So all we have to do is square that, and now we have an integral that has only u's in it. A 1 minus u squared, and a u squared du. And then we could actually go through the process of integrating with respect to u. So we found a substitution. We may not have known in advance which substitution we were going to use, but we found one that would work because we can do this conversion. Well, actually, we'll continue the action. We'll do the actual problem on the next page. Okay, we're to, for real now, evaluate sine to the fifth x, the integral of sine to the fifth x cosine squared x. And let me remind you again, the secret here is the odd power. The odd power, because if we name the other function our u, then when we look at the derivative of u, and actually I see on the previous page, I should have had a negative value, shouldn't I? Sine x. I'm sorry that I made that mistake on the previous page. We'll fix that now. Anyway, the fact that we've got an odd power means we can borrow one of those powers, and we'd still have an even power of a function, sine in this case, and even powers can always be converted to the other trig function. Even power of cosines can be converted to sines, even powers of sines can be converted to cosines. So as we started a moment ago, what I'm going to do here is I'm going to let u be cosine of x. And then du is actually negative sine x dx. That's where I made my mistake a while ago, because the derivative of cosine x is negative sine x. So our integral will then look like this. We'll have the integral of sine to the fifth, sine to the fifth x, cosine squared x dx, that's a square. I'm going to replace cosine x with u. So this becomes the integral of sine to the fifth x, u squared dx. Now I need to create the du, and so I borrow one of the sines, okay? That is, I'm going to write this as sine to the fourth x times sine of x. So I do it in this fashion. But I actually need a negative sine x dx to have a du. So I'm going to put a negative value on a negative factor on the outside of the integral sign. Okay, and then I'm going to, of course, have a negative on the inside factor. And so now what I've got is my du right here. That's my du. So we'll do that replacement. We have the negative of the integral of sine to the fourth x, u squared du. Now, the problem is we need to convert the rest of this into u information. And we saw a moment ago, because, let's come over into this position, because sine squared x, or sine to the fourth x, can be written as sine squared squared, and sine squared x can be written as 1 minus cosine squared x, then what we really have here in this position is the negative of the integral of 1 minus, now because I'm calling cosine of x u, then this is really 1 minus u squared being squared. So in this position we have 1 minus u squared squared times u squared du. Now, it's not a great deal of work to expand this. That is, when we square 1 minus u squared. So we're going to do that. When we do, we'll get 1 minus 2u squared plus u to the fourth. And outside, we still have a u squared du. Now we can easily multiply that u squared out, okay? And we would end up with the negative of the integral of u squared minus 2u to the fourth, that is u squared times negative 2u squared, and a u squared times u to the fourth is plus u to the sixth in this position, isn't it? And so we can easily integrate that. Well, as we integrate it, let's see what we get. Okay, we'll have an indefinite integral results. Well, the integral of u squared is 1/3 u cubed minus the integral of u to the fourth is 1/5 u to the fifth. So this is 2/5 u to the fifth in this position. Okay, plus the integral of u to the sixth is 1/7 u to the seventh. And of course, plus our constant of integration. Now we have that negative sign in front of the expression, so we'll distribute that negative sign and we'll resubstitute, remembering that u is really cosine of x. So this becomes minus 1/3 cosine cubed x plus 2/5 times cosine to the fifth x minus, remember we're distributing that negative sign, 1/7 instead of u to the seventh, cosine to the seventh x, plus our constant of integration. So that worked out very cleverly and very nicely for us. Let's look at another example. Okay, in this problem we're supposed to evaluate the integral of cosine cubed x times the square root of sine x with respect to x. And once again, notice that we have an odd power, and that becomes important because when we have an odd power, we can borrow one of the powers and still have an even power left. So we would experiment. I mean, the truth is we would experiment, but most likely we're going to need to borrow that odd power. If we choose, here's the idea. I'm sorry for stammering here. If we choose u to be cosine of x like we did in the last case, then we're going to be left with a du is equal to a negative sine x dx, and we don't have anything to work with. I mean, because we have a square root of sine x, and we don't have anything to work with. On the other hand, if we choose u to be the sine of x, then du would be cosine of x and dx. And the secret here is, since we have cosine cubed x and a dx, okay, we're going to have that. We can, and other stuff in here, right? There's some other things in here. But we can break this down into a cosine squared x, along with this other stuff, times a cosine x dx. And so this can be turned into the du, but the secret is this can be turned into sine stuff. Okay? And then we have our original replacement for sine and u's. Then we can get this in sine stuff and replace that with u stuff as well. So it's really useful in this case that we make this substitution. Okay, so that's what we're going to do. We're going to evaluate, so let's set up our problem, the integral of cosine cubed x times the square root of sine x dx. Now way over here, I already started this, I'm choosing to let u be sine of x. And so du is going to be cosine x dx. So when I come over here to do my work, okay, I'm going to write cosine. I'm going to borrow one of the cosines. So I'm going to write this as cosine squared x times the square root of sine of x times cosine of x dx. Now, this ends up being the du. And under here is a u. So what we have at this point is the integral of cosine squared x times the square root of u times du. So now the issue is to rewrite this so that it's about u. But cosine squared x, using the identity that it's the same as 1 minus sine squared x. And we have square root of u du. Now the significance there is that u is sine of x. So this is nothing more than the integral of 1 minus, instead of sine of x squared, u squared, times the square root of u du, and you see how clever this is now. Now the only thing I would do to start to finish this is I would write the square root of u as u to the power 1/2. And that would allow me to have just regular powers of u as I multiply this out. So I've got the integral of u to the 1/2 times 1, that's just u to the 1/2, minus u to the 1/2 times u squared. And u to the 1/2 times u squared is actually u to the power 5/2. And so that's what we need to integrate. Well, the integral of u to the 1/2 power is going to be u to the 3/2 power with a factor of 2/3 in front of it, minus the integral of u to the 5/2 power is going to be u to the 7/2 power with a factor of 2/7 in front of that, plus our constant of integration. And then, of course, we'll replace u with sine of x. Pardon me, I'm having a bit of a thought here. So we'll have 2/3. Rather than u to the 3/2 power, we'll have sine to the power 3/2 x minus 2/7 instead of u to the 7/2 power, that's sine to the power 7/2 x. And of course, there's multiple ways that we could actually write that. But I think for now, we'll leave it in this fashion. Okay, let's look at an additional problem. We'll do that on the next page. You see here we're to evaluate the integral of sine cubed x with respect to x, which is different than the previous two examples because we only have one trig function, but it's similar from the point of view that we have an odd power. Okay, so that's still happening to us here, and there's really not much choice for what we can do here, I don't believe, in terms of how we can make this substitution. Or is there? Because we kind of have to look here. Suppose we make u, because that's the only trig function we see, suppose we make it sine of x. Then du would be cosine of x, and we see no dx, and we see no cosines in front of us. But if instead we note that rather than what we could do is we could say sine cubed x is sine squared x times sine of x. And sine squared x is 1 minus cosine squared x. So we would have this, wouldn't we? Well, in that circumstance, we could let u actually be cosine of x. And then du would be negative sine x dx. And we've got the sine x to work with, and we could make this 1 minus u squared, couldn't we? Okay, so I think that should be our plan. We'll let, as we started, we're going to evaluate sine cubed x with respect to x. But we're going to be clever in advance, and we're going to write this as the integral of sine squared x times sine of x dx. And we're going to write sine squared x as 1 minus cosine squared x. So we still have all of this written. And now we're going to make our u substitution in this fashion. We're going to let u be the cosine of x. So du will be negative sine x dx. And so we need a negative sine x there, so we'll begin with a negative. We'll put a negative 1 factor on the outside of the integral so that we can have a negative 1 factor on the inside of the integral, and we'll put it in front of that sine of x. So here we have our du, and of course here we have now 1 minus u squared. So we have the opposite of the integral of 1 minus u squared du. We can easily integrate that. The integral of 1 with respect to u is u. The integral of u squared is 1/3 u cubed. Don't forget our constant of integration. And so we can write this then as negative u, but u is cosine of x, plus 1/3 u cubed. But u is really cosine of x, so we'd say plus 1/3 cosine cubed x plus our constant of integration. So that shows you several clever things that we can do. Now, in each of these cases, we have had an odd power. And so we need to worry about what happens when neither of the powers is odd, that we don't have an odd power. All powers are even. Then we have to deal with things a little differently. As we continue with integrating this form, a product of sine and cosine to powers, what happens if neither power is odd? And in all of the cases that we've seen so far, one of the two powers was an odd positive integer. So, for example, and this is one that we'll actually do here in a moment. For example, the integral of something as simple as sine squared x cosine squared x dx. I mean, there's multiple approaches to this, or something. Let's just say the integral of cosine to the 4th x. Earlier we had an odd power of just one trig function. The point here is neither one of these cases has an odd power of a trig function of sine or cosine in it. And we have to rely on some more trig identities. So let me make sure that you recognize these trig identities. We will use these frequently in this section. And one is the half angle formula. And for instance, the sine of x or a, I'm using a here just so I can identify it later on. The sine of a over 2, remember, is either plus or minus. It's one or the other. It depends on the angle a. But it's plus or minus the square root of 1 minus the cosine of a alone, divided by 2. Now, what would happen here, this is what we're mostly interested in, is if we have the sine squared x. See, if we have sine squared x, this is called a power reduction formula, power reducing formula. That's what we're getting ready to write. Well, if we look to the left, when we square sine of a over 2, then it wouldn't matter whether it's a plus or a minus. We'll get a positive result, and we'll be squaring that square root. And so what we'll get is the radicand itself. We'll get 1 minus the cosine. Now notice, on the left, we have the cosine of a, and the significance is this a is double what we're taking the sine of. A is 2 times a over 2. So what we have the cosine over here needs to be double what we're taking the sine of, and so double x is 2x, and that's all divided by 2. And many times I'll write this as 1/2 times 1 minus cosine of 2x. And we've actually seen this in previous sections in our book. This is called a power reducing formula, so we can convert sine squareds, or even any even power, because we could do this multiple times, but sine squareds into cosine to the first power, but the argument changes from an x to a 2x. And in a similar fashion, we have a similar identity, half angle identity for cosine. It says cosine of a over 2 is plus or minus the square root of 1 plus cosine of a divided by 2. So if we square cosine of x, then we'll end up getting 1 plus cosine, the double of our x, which is 2x, all over 2, which we can write as 1/2 times 1 plus cosine of 2x. And one other one that we may have come in handy for us occasionally is using the double angle formula for sine. The sine of 2a, remember, is 2 times sine of a times cosine of a, which tells us that look, we can take this, if we had sine of x times cosine of x, if we had that, then think of that as being this part, okay? So if we solve for this, we'd have a 1/2 in front of the sine of 2a, but now remember, in this case, so that would be a 2x, wouldn't it? So it'd be 1/2 times the sine of 2x. So we can convert sine x cosine x into 1/2 of sine of 2x. So we can eliminate one of the trig functions, I guess, is the idea behind this. Okay, so let's look at our next example. And it was one I was alluding to above. Example, I guess this is example 4. And we're to evaluate the integral of sine squared x cosine squared x dx. Now, as we're getting ready to do this, let me write the problem down here. As we're getting ready to do this, the problem with what we did previously, see, and maybe we'll continue this on the next page. The problem with what we did previously, if we name, say, u to be sine of x, well, there's nothing wrong with that. Our du would be cosine of x, but the problem is we would have the integral of u squared and, excuse me, dx, and we'd have to take cosine squared x and write it as a cosine x times another cosine x dx so that we get a du. And then we have a hard time dealing with cosine x alone. See, how are we going to convert that into u's? If it was cosine squared x, we can convert it into 1 minus sine squared x and then into u's. But we don't have that. And so that's the reason this falls apart on us. So what we're going to do here, or an approach, and it's not the only approach, is that I'm going to write sine squared x in terms of, here's what I'm going to do. I'm going to write sine squared x as 1/2 times 1 minus cosine of 2x. So using that, and I'm sorry, let me, actually, let me go to the next page because I've kind of messed up my space here, I think. Let's go ahead and see if we can finish it. I'm going to try to block this off, and I apologize for getting so crammed in here. I'm going to convert cosine squared x using the power reducing formula above to simply 1/2 times 1 plus cosine of 2x. And of course, we have a dx. So let me put the equal sign here and rewrite all of that because it's a big mess. Okay, so sine squared x I'm reducing to just cosines in this fashion. It's 1/2 times 1 minus cosine of 2x. And cosine squared x I'm reducing the power on it to just first power again of cosine, but it's 1/2 times 1 plus the cosine of 2x with respect to x. Now, I have a 1/2 factor in front of both of those. I'm going to factor out, so I have a 1/4 times the integral of 1 minus cosine of 2x times 1 plus the cosine of 2x with respect to x. Now here I can easily multiply those out. Here I would, if we multiply those out, we're going to get what? 1 minus cosine squared of 2x. So we're going to get. Now the problem with that is cosine squared, I have a problem integrating. So I'm going to use the power reducing formula now on cosine squared of 2x. So here's what I'm doing. I'm reducing cosine squared of 2x into 1/2 of 1 plus the cosine double 2x. So it becomes a 4x, doesn't it? So that's what cosine squared 2x is, and I can put that in, of course, this position. Okay? So I end up with 1/4 times the integral of 1 minus 1/2 times 1 plus cosine of 4x. Whoops, 4x with respect to x. Well, I've got another parenthesis there. And we'll distribute that negative 1/2. Okay, we'll distribute that negative 1/2, and so we'll have the 1/4 that's out here, and we'll have the 1 in the beginning, and then we have a minus 1/2 times 1, and a minus 1/2 times the cosine of 4x. Now the 1 minus 1/2, we can certainly simplify, can't we? So this becomes 1/4 times the integral of 1/2 minus 1/2 times the cosine of 4x with respect to x. Now, if we wanted to, we could actually factor a 1/2 in both of those terms. That would be all right. So we'd have a 1/8 times the integral of a 1 minus cosine of 4x with respect to x. And each of those things we can integrate just fine. So here's our 1/4. The integral of 1 with respect to x, of course, is x, minus the integral of cosine 4x happens to be a 1/4. We can do this by substitution, but I hope that we're all right with that now. 1/4 sine of 4x plus our constant integration. And so now we can distribute. Whoops, except this is a 1/8 here, isn't it? My bad, a 1/8. I factored out that 1/2 previously. So when we distribute, this becomes a 1/8 x minus a 1/32 sine of 4x plus our constant integration. Now, it's not the only way to do this problem. Let me, on the next page, let me show you an alternative approach. And there may be several alternative approaches. One that comes to my mind while we're on this. I don't know that this would work in very many situations, but I'm noticing since both of my powers are exactly the same, what I could have done is I could have said, okay, the integral of sine squared x cosine squared x dx could be written as the integral of the sine of x times the cosine of x and square that product. And the usefulness of that is, remember on the previous page, we wrote down, okay, that the sine of x times the cosine of x could be written as 1/2 times the sine of 2x. And so we could replace inside those brackets, we could replace that with a 1/2 sine of 2x. And of course the brackets are being squared. Now we have only one trig function, and of course we could apply the squaring to that one single trig function, so we'd have the integral of 1/4 sine squared of 2x. And of course the 1/4 could be factored out, and we would have to deal with the integral of sine squared of 2x. Well, we don't have an easy way to integrate that, so now what we have to do is use the power reduction formula. That is, sine squared of 2x is 1/2 times 1 minus the cosine of double the angle 2x. When we double 2x, we get 4x. So we can replace sine squared with something that we can actually integrate. So we could replace this, look at the integral of a 1/2 times 1 minus cosine of 4x. I'm going to forego those extra parentheses because it's making it hard to read. And now I can factor that 1/2 out, and I have a 1/8 times the integral of 1 minus cosine of 4x with respect to x. And you can see that when we integrate 1 with respect to x, we get x. When we integrate cosine 4x with respect to x, we get minus 1/4 sine of 4x plus our constant integration. And so we get exactly the same result, 1/8 x minus 1/32 sine of 4x plus our constant of integration. So it's an alternative form that I don't know that would always work here. I mean, in all situations, but it happened to work here. Okay, let's, and so this maybe will give us an idea of how we would deal then, and I don't know that I'll go through the whole problem, with the single sine or cosine to an even power. Now we've already seen that if we have an even power, we had an even power here, didn't we? When we have an even power, we can convert it to a first power, or a power 2. What if our power was greater than that? That is, if we were asked to evaluate the integral of cosine to the 4th x with respect to x. Again, no odd powers, but we can deal with this in this fashion. We can think of cosine to the 4th x as a cosine squared being squared. And then we can use the power reduction formula on the inside. That is, we could rewrite the inside so that it was a 1/2 times 1 plus cosine of 2x. And that's what's being squared. And then we could proceed from there, okay? We would have a factor of 1/2 in front, and that being squared, and so we'll factor that out after we square that 1/2 as a 1/4, and then we'll have a 1 plus cosine of 2x, this being squared with respect to x, and so we would go through the business. Let's finish this out at least a bit further. We would actually need to do this squaring of 1 plus cosine 2x. Well, if we do, we'll get 1 plus 2 times cosine of 2x plus cosine squared of 2x. And then we would need to use a power reduction formula on cosine squared of 2x here. See, cosine squared of 2x, we can't integrate that. But we can write it as 1/2 times 1 plus the cosine of double 2x, which is 4x. So we could put all of that in this position here. So we have 1/4 times 1 plus 2 cosine of 2x plus 1/2 times 1. So I'm looking above. See, this is 1/2 times 1, which is 1/2, plus 1/2 times the cosine of 4x. So we have a 1/2 plus a 1/2 times the cosine of 4x in this position. Whoops. And that's what we're integrating. Now, the 1 and the 1/2 could be combined to get 3/2. And then we could certainly integrate these two pieces because they're just cosine to the first power. We'd have to use maybe some substitution, know how to do this. But the result we should get, if you would like to check it, will be 3/8 x plus 1/4 times the sine of 2x. And of course that has something to do with the integral of cosine of 2x, plus 1/32 times the sine of 4x, plus our constant of integration. And I'm more interested at this point in the process that we went through to get to this stage, and I'm sure that from here you could go further like I have done. I did it in one big step, but you could fill in the other steps. Now, as we proceed, we're going to change from products of sine and cosine to products of tangent and secant. And they will give us yet a different twist, but similar to the kinds of things that we've already been doing.